right, we have Phil Koshute. He's from Hopkins University Applied Physics Lab. He's a data scientist and statistical modeler. He has degrees in mathematics and operations research and is currently pursuing a PhD in applied statistics from the University of Maryland. So take it away, Phil.
Thank you. Sorry for the frog. Good afternoon. Thanks for coming to my talk. As said, my name is Phil Koshute. I'm a data scientist at Johns Hopkins Applied Physics Lab. Today, I'm going to talk about how we've explored different options for comparing time series. Our application is a project where we're implementing a device that estimates the core temperature of military working dogs. So I will be showing pictures of dogs in a minute, and thereby aims to reduce their risk of heat injury. And I'll be describing data from some in-house tests that we've done to validate a key component of this device. And these tests are ultimately aimed at making our testing process more efficient without sacrificing rigor, and thereby enabling these devices to be fielded sooner. Let's see. Okay. We're grateful to have this work, which extends to a whole team at APL, funded by United States Army Medical Materiel Development Agency. But at the same time, just want to say that this presentation is not intended to be the official perspective of that organization. Okay, so here's an illustration of our problem. So we've got two time series, one corresponding to a reference device, and then the other one corresponding to measurements from our own test device. We want to rigorously compare them and assess them for a sufficient level of similarity, and thereby determine whether the component from our test device is ready for more sophisticated and operationally realistic field testing. Now, notice the notions of similarity or sufficiency, neither of them are necessarily well defined. So this leaves us open to a variety of different analysis options. So I'm going to talk about that in the second half of this presentation. First half, I'm going to just introduce you more to the problem. I'm also going to talk about potential strategies for handling the complications that arise from having timestamps that aren't necessarily aligned, and then also a lack of independence within the data. So within this objective of trying to streamline our test process, I'm going to give some background on the canine thermal model, so we call our device, how it originated, some details on the underlying algorithm, the data that we're collecting as part of our in-house test to ensure that that component is being measured, it's measuring what it should measure correctly, as well as some ideas on how we're analyzing the data. And again, that'll be the meat of the presentation. So ultimately, this amounts to dogs, devices, and data. Okay, so as you may know, there are hundreds of military working dogs that are deployed on missions supporting a variety of branches for the United States Department of Defense. And if you look, if you think about where the current global conflicts are and overlap those with this map of global temperatures, it's easy to see that some of these missions are going to be in places that are very warm. So as a result, the military working dogs are vulnerable to elevated core temperatures and then heat-related injury. The handlers are generally very good at observing the dogs and knowing when they need to stop, but you can imagine during a mission, they're focused on lots of different things. So any sort of aid to provide them additional situational awareness and help them to know how to best tend to their dogs is a real benefit. So in response to this need, the United States Army developed an algorithm about a decade ago that estimates a dog's core temperature without the need for invasive monitoring. This algorithm is based on environmental factors and then the dog's metabolism. I'll say a little bit more in a minute about how we're estimating the metabolism. And this algorithm can be useful both for alerting the handler during a mission for when the dog needs to slow down, be pulled back, and then also after the mission for how long the dog may need to cool down before going on another mission. Okay. So among the inputs to the algorithm, one of the crucial ones is the dog's metabolic activity, especially when they're running around. So that's what generates heat on the inside of the dog. So as with core temperature, though, the algorithm doesn't rely on direct measurements of the metabolism, but instead we're estimating it. This is straight from the algorithm that was developed. Estimating it with the variation in the dog's acceleration over time. So we're measuring that with an accelerometer that's on the dog. So you can think of the dog starting and stopping many times, and that would be reflected through the variation in the acceleration. So in summary, we're using this variation in acceleration to estimate the metabolic activity, which is then a key input into our algorithm that estimates the core temperature change in the dog, which then as you carry forward, you can estimate what the dog's core temperature is and tell when it's getting too high. Okay, so in order to move toward deployment, the algorithm was initially implemented by MIT Lincoln Labs as a device worn on the dog as a collar. So currently my organization, APL, is leading an advanced development phase in which we've added an Android interface that's wirelessly connected to the sensor that the dog wears, most likely still as a collar. And we're also validating the system for its operational readiness. So a central part of validating the system is, of course, to test it on actual dogs. And this would involve checking the dog's core temperature through invasive monitoring, and then comparing it with the device's estimates. However, as you can imagine, these field tests require a lot of labor, time, money to both to plan and then to carry out. And even more importantly, they interrupt the dog's training regimen. So we want to minimize those tests. And in order to do that, we are complementing them with less expensive in-house tests of the specific components. And today I'm going to focus on the tests for the accelerometer. So for instance, rather than waiting until a field test to discover that the accelerometer is inaccurate and then losing the chance for a full day of field tests, we're separately testing that accelerometer in-house, hopefully enabling issues with that component to be discovered prior to field testing. So in this sense, again, we don't have formal requirements. We're just trying to obtain assurance before we go into the field test, and this leaves room for lots of different analysis approaches. And I'll just say we've done a lot of research on how to compare these time series, but I don't consider myself an expert, so perhaps you'll be watching me go through and you'll have ideas of how we could have done this. I'd be very happy to hear that at the end if anything comes up. Okay, so before diving into the data analysis, we're just going to make a quick note on how we're collecting the data. We're using what's called an electrodynamic shaker table. This is in the same lab where APL, my organization, has tested spacecraft. You can see in this picture one spacecraft that's currently orbiting the sun and taking measurements. It's the closest man-made object I think it's ever gotten to the sun. We are through these tests, we're subjecting our device to a specific acceleration profile with a sinusoidal variation at different amplitudes, and I'll show you more about that in a minute. And then we're also measuring the same at the same time measuring with the reference device that provides us the ground truth. And it's by comparing again our time series for the device with the time series from the reference accelerometer that we're trying to gain assurance. Okay, so here's a look at that sinusoidal profile. It just continues to go up and down on that table. Here's a better picture zoomed in for the first 3 minutes. And then we repeat this pattern multiple times in order to have more data for our analysis. So thinking about the challenges that we have with analyzing the data, there's a couple ways we can process it. I can look directly at the raw data. And you probably didn't catch this because I was going through quickly, but within the algorithm, we look at the variation over a 5-second interval and over a 1-minute interval. So we can instead look at for each time series, break it into the 5-second interval and take the maximum acceleration value, because that's really what drives that variation, or do the same thing over a 1-minute maximum. And you'll note that I'm showing you simulated data just because it's cleaner to show that these different concepts. So quickly, I'll harken back to some of the challenges that we're facing. We are not guaranteed that the timestamps are aligned, so we can't directly compare one measurement to another from the 2 time series. And then also there's a substantial amount of autocorrelation within the time series, where if you take one measurement and compare it to the preceding measurement, there's a high amount of correlation. You can see as you lag different numbers of measurements, it takes a while before you get down to a smaller amount. So this directly would come into conflict with a lot of statistical tests that we would perhaps consider. So, and then the last thing would be we have to decide between hypotheses that assume no difference as the null hypothesis and test for differences, or if we instead consider hypotheses that assume some level of difference and arbitrarily set equivalence margin and instead test for equivalence. There's pros and cons to both of these. And I'm going to be going through examples of them in a minute. Okay, so given all these considerations, options include, we're going to look at paired values versus unpaired values, raw values versus binned values. We'll look at compare individual points. We can compare distributions of points. So in the next few slides, we're going to focus on comparing with hypothesis tests. Those are not the only ways to do it. I'll highlight a couple other alternatives at the end, but just for the sake of time, I'm going to focus on hypothesis tests for today. And some of them, as I go through them, you immediately flag them as unsuitable because of how our data violate their assumptions. But I'm going to show them to you anyway, just to show the progression of the different test options, and then also to highlight the trade-offs in satisfying the assumptions of the test with the objectives that we're trying to get from our analysis. All right, so all of these next few slides have the same layout. I'm going to be showing you the version of the simulated data that we're comparing, the test null hypothesis. So here it's that the difference in mean is 0, and then the test statistic is that the difference in the means. Probably, yeah. So in the interest, I'm going to be going fairly quickly, so you won't be able to absorb too much of it, but I'm going to show you some example code and then the results from the particular test, and then also highlight some of the considerations of that test and how well we meet the assumptions. So for instance, with this test, this is sort of step 0, looking at this t-test of the unpaired data. We're just lumping together all the values from each time series, basically into 2 piles, and treating them as separate samples. So this utilizes all the available data, but it fails to incorporate the fact that we're comparing 2 samples that have been tracking the same experiment, so they're being measured simultaneously. So instead, let's see, click, too many clicks. We could instead address that non-alignment of the timestamps by taking those 5-second maxima. And this way we have the maxima are aligned within those intervals. So this reflects the simultaneous measurement, but then we have another assumption that we're not meeting, that's of the independent data. Oops, too many clicks. Okay, so we could make the data more or less independent by only considering, instead of the 5-second intervals, we could look at 1 data point for each of these steps. So these are 1 minute each. And those have a lot less autocorrelation. So one problem with this approach, though, and you're seeing a pattern here. I'm showing you got pros and cons with each of these approaches, and if you're not tracking the individual results, I'll have a slide at the end where we can kind of take them all in together. But you can think of a scenario where we've got 0 mean, but the variance is high. You know, we have +2, -2, +1, -1, and that would come out as a 0 mean. But it would falsely give us the assurance that they were the 2 time series were matching up with each other. So instead, we could just do a test on 1 sample of the absolute difference between the 2 time series. But going back to the assumptions, all these t-tests have assumed normally distributed data, which we don't necessarily have. So in order to account for that, we could use the Wilcoxon test, either with the absolute differences, again with 1 sample, or with the taking the maxima over the 1 minute interval. So here we've gotten around the assumption for assuming normality, but we haven't yet directly tested for equivalence, which is what we really want to show in considering the 2 time series. You're pushing it for me. I like this.
I think the clicker stopped. We're getting some IT curveballs here. I've just been watching your face.
I wondered if you're really good at anticipating.
Gaslighting you just. You're gonna lag.
Not as many clicks from here on.
Keep doing it, it's working.
You just gotta emphasize.
So testing for equivalence, we just take the 2 one-sided t-tests where we look at equivalence margins, and we want to disprove both null hypotheses, so we're above or below. And here it's the half of the standard deviation of the data. Here we're directly checking for equivalence, click, but we're no longer using all available data. So we could, going full circle, we could instead look at comparing the distributions of the data. We click, click, click. We no longer are looking though at, the fact that we've measured these 2 time series simultaneously. And this is the last of the blitz of these different methods. So we can go to the next slide and compare. So you can see we get a variety of results here. Variety of tests, variety of conclusions. So how do we make sense of this? This is still something that honestly we're working through, trying to refine our approach as we run these tests and move towards field tests. So ultimately, the question amounts to, do we have enough assurance to proceed with the field tests? And at the end of the day, it depends on the combination of these results. And I wouldn't recommend just taking a majority vote, but it kind of, you get different perspectives from each of the tests and which assumptions are important. So combining those results with the project's accuracy requirements and how much risk we're willing to, as we're going into these more involved field tests. Okay, so just before I wrap up, just a quick note on using power analysis for the test planning. So you take one or more of these tests and specifying a targeted power that we want to be able to detect the difference within the 2 time series. And this is particularly important if we're going to use the approach where we're testing for differences. We want to have a reasonable chance to detect that difference in order to get some assurance of that similarity. So specifying a power, a significance level, and then making assumptions about how much the data are going to vary. That then tells us how many samples we need. Assuming we get 1 sample for each of those steps within the profile, that tells us how many times we need to run the profile. I've focused on hypothesis tests, but there are lots of different options in this question of comparing time series. So functional data analysis, I think there's going to be some talks tomorrow on that. It's really intriguing technique, but I don't know that it applies here because we don't really have a progression between different experiments of from which we get the time series. Something simple would just be to take the correlation between the 2 time series, and then dynamic time warping is a possible approach for correcting for the non-alignment of the timestamps within the time series. Okay, so in closing, thank you very much again. We're using the tests of the in-house tests of the accelerometer as a way of uncovering potential issues prior to the more expensive field testing. And there's various options for comparing the time series from our device with the reference device, and I've focused on hypothesis tests, but there are other options. Our current approach basically involves considering the test results, getting some sort of pseudo consensus, but also in conjunction with where we are in the timeline of the project. So this is a very practical challenge, and ultimately the test, when we get to the field test, if our accelerometer works correctly, then we know we've done enough tests, but so it's kind of the iterative process. So hopefully I've given you some ideas for how to compare time series. Again, maybe you had an answer right away. From what I can tell, this is a relatively open question though, for how to take 2 time series and compare them rigorously. So thank you for your attention. And happy to take questions or ideas.
You have time for a couple of questions.
Okay. I missed the beginning, so forgive me if you mentioned this, but fast Fourier transform to look at amplitude and frequency maybe is another approach if that would be important to match those, especially the amplitude since you're looking at accelerations.
Right.
Just throw that out there.
Okay. Thank you. Yes, sir.
You had it on slide 30. I would encourage you to explore the functional data approach. Do you know Joe Warfield?
Yes, I do.
So Joe would be a resource. And I mean, I know he's done a fair amount of that.
Okay.
And so I think, this idea of using all of the data and breaking it into pieces where you've got sort of shape versus the attach the badge within it.
Yeah.
I've seen it applied to glucose monitor data in humans. where they've been able to model aspects of it. So don't know where the ultimate goal is with it, but I would think that would be a good
Okay,
avenue. to
Yeah,
pursue.
I dabbled in it, but at your suggestion, I'll take another look.
And what were the pros or cons of using the sinusoidal versus something that's more operationally representative of the accelerations the dog experiences?
Yeah, we were just trying to get, and cover the range of possible acceleration values, really, and the changes in them. Yeah, you didn't expect the dog to.